Hi everyone, Prof. Chris here. In today's video, we will be covering chapter 5.7, Simplify and Use Square Roots in the OpenStax Pre-Algebra textbook. Now, the core learning objectives for this video are to simplify expressions with square roots, estimate square roots, approximate square roots using a calculator, simplify variable expressions with square roots, and then use square roots in applications. So let's go ahead and get started with this first introduction question. So the question I'd like to get started with is, how do we solve the following problem here where we have a big number 5 next to a small little number 2? What's this type of problem actually called as well? And then if I was to solve this problem, how would we actually reverse the solution? So go ahead and pause the video here and write down some of your thoughts for this initial question. So this particular question here is what's called 5 squared. It is an exponent type problem. So when I look at the big number 5 and that little number 2 here, they have specific vocabulary words tied to it. The big number is called the base number, and the little number 2 is what's called an exponent or a power, or if you're in England, it would be called an indice, right? So what this is showing is how many times to multiply the base number by itself. It's repeated multiplication. So 5 squared can actually be noted as 5 times 5, which is equal to 25. Now, like every operation in math, there is something that reverses or undoes that operation, that solution. So if I think about addition, I would think about subtraction being what reverses it. So for example, if I was to add 5 plus 2 and I get to 7, I could reverse this by doing 7 minus 2 and I get to 5. Likewise, I can multiply 5 times 2 to get to 10. And if I wanted to reverse what I just did here, I would do 10 divided by 2, and I would get to 5. So exponents also have something that reverses or undoes the operation that we are using, and this is called a square root. So we use the square root because squaring and taking a square root are opposite operations. So 5 squared, 5 times 5 equals 25, is reversed through this symbol right here. The square root of 25 then gives us the base number 5 here. So do you know why we use the word square here? Well, it's kind of illustrated in the image on the right-hand side of our screen here. If we construct a square with 5 tiles on one side and 5 tiles on another side, and we were then to multiply that against each other, 5 times 5, we would get a total of 25 squares inside of it. That is the area then of this square. So when then I go to define a square root of a number is a value that can be multiplied by itself, like 5 times 5, to equal the original number here. Now, a perfect square is a number that results from multiplying a whole number by itself. So examples of perfect squares are the following. We could have 1 squared, which is really 1 times 1, which equals 1. So 1, these are the perfect squares here. So we'll say perfect squares are listed below here. So 1 squared is 1. 1's a perfect square. 2 times 2 equals 4. 4 is a perfect square. 3 squared, which is 3 times 3, which equals 9. 9 is a perfect square. 4 squared, or 4 times 4, equals 16. That's a perfect square. 5 squared, 5 times 5, which equals 25. 25 is a perfect square. 6 squared, which is 6 times 6, which equals 36. That's also a perfect square. And you could continue on for an infinite amount, right? So perfect squares are the number when a big base number multiplied by itself gets us to that number. Now, what happens when you are squaring a negative number? So when we multiply two negative numbers against each other, the product is always a positive, right? A negative by a negative is a positive. So the square of a negative number is also always positive. So if I have positive 2 squared, this is 2 times 2. My answer is equal to 4. On the other hand, if I have negative 2 squared, this equals negative 2 times negative 2. That gives me a positive 4 as well. Another example of this, if I have 3 squared, that is 3 times 3, which equals 9. Or if I have negative 3 squared, that is going to be negative 3. Actually, I don't need to do that. We'll do negative 3 times negative 3. That also equals a positive 9 here. Now, if I look at square root notation, what we have here is first a radical sign. So that is the symbol that we have in front of it. And then we have the m variable in this case. That is what's called the radicand. That's the thing that's under the radical sign. So the m could represent any number. If I look at the perfect squares again, and I was to do the radical or square root of 1, that is equal to 1. If I did the square root of 4, that is equal to 2. If I did the square root of 9, that is equal to 3. If I did the square root of 100, so skipped a bunch, that's equal to 10, and so on and so forth, right? So that radical sign is what this symbol is called, and then the number underneath is called our radicand. Now, if we want to find the negative square root of a number, we need to place a negative then in front of the radical sign. That's important. So I could write the square root of 1 with a negative in front, and I would get negative 1. If I wrote the negative square root of 4, I'd get negative 2. If I wrote the negative square root of 9, we get negative 3. If I wrote the negative square root of 16, we'd get negative 4 here. Okay, so if I want to have a negative answer, we need to put the square root in front of the negative symbol. Now, this brings up an interesting question. Can we simplify something if the negative is actually under the radical sign? So in other words, can we simplify the square root of 96? Well, basically what this question is asking, is there a number that when you square it equals negative 36? So in other words, if I was to write it out, what number when squared equals 36? Well, or excuse me, negative 36. Well, any positive number squared is positive, and any negative number squared is also positive. So there is no number that can be negative 36. So we would call this a no solution type problem, or if you wrote it on your calculator and it came back, you'd either get an error message maybe, or you might even get the word undefined. So undefined is also a way to describe something that does not have a solution in this case. So the negative symbol cannot fall under our radical sign. For it to be negative, to get a negative number, it would have to fall on the outside of it. Okay, so let's test our understanding here. Make sure we're understanding this correctly. So I would like you to go ahead and simplify the following. Can you simplify square root of negative 49? And can you simplify negative square root of 49? Okay, well, in this case, we have a negative symbol under our radical sign. So this is a no solution type problem. There is no number that can be multiplied by itself to get to negative 49. On the other hand, this one, we would take first the square root of 49, acting like a grouping symbol, and we put positive 7. And then the negative falls on the outside of the square root symbol, so then we would drop that into our answer here. So negative square root of 49 is equal to negative 7 here. Now let's look at a series of questions that asks us to use square roots and the order of operations. Key thing to note here is we treat the radical sign as another grouping symbol, meaning we have to solve under the radical sign before we do anything else. So question 1, we have the square root of 9 plus the square root of 16 here. In this case, we are going to do what's under each sign first, and then sum or add these together. So the square root of 9 is positive 3, while the square root of 16 is positive 4. Then we add these two numbers together, 3 plus 4, and we get an answer of 7. On the other hand, if I have the square root of 9 plus 16, we would do what's under the grouping symbol, under the radical sign first, which is the addition piece. So we would do 9 plus 16, which becomes square root of 25. And then we would take the square root of 25, and that happens to be a perfect square again. So we would get positive 5 as our result. The next skill we're going to look at is how to estimate square roots. And we're going to estimate square roots by asking what are the two consecutive whole numbers a square root falls in between. So first off, when we look at consecutive whole numbers, we then need to understand what our perfect squares are. So here's our listing of perfect squares. Okay, so we have a listing of our perfect squares now. So square root of 1 equals 1, square root of 4 equals 2, square root of 9 equals 3, so on and so forth. So now let's go ahead and write square root of 32. And we're basically trying to figure out, okay, what perfect square is less than 32 and what perfect square is bigger than 32 here. So if I look at the listing here, I see that square root of 32 is going to fall in between the square root of 25 and the square root of 36. In other words, if I actually took the square root of 25 and 36, I'm going to get a whole number 5 and a whole number 6. So 32, square root of 32, and you could check it on your calculator. Oops, not square root of 6. Just a regular whole number 6 here. Square root of 32 is going to fall in between 5 and 6 here, right? Okay, let's try square root of 68 now. Okay, so let's go ahead and put square root of 68 in the middle here. And then less than and greater than symbol. And then looking at 68, I can see that it falls in between square root of 64 and the square root of 81. In other words, if I then simplified these two square roots down, we would get 8 and we would get 9. So square root of 68 is going to fall between 8 and 9. And since 68 is also closer to 64, square root of 68 is closer to 8 than it is to 9. Okay. All right. So that's estimating each square root between two consecutive whole numbers. The next set of questions asks us to approximate square roots, and we're going to approximate using a calculator. So we're asked to use a calculator to approximate each square root and round to 2 decimal places. In other words, round to the hundredths place. So we're looking first at square root of 27. So on your calculator, you will usually be given different sets of symbols. Every calculator looks slightly differently, but you're going to look and locate this particular square root here. Now the square root here, this guy is a radical sign, it's technically an nth root, which can stand for a cube root. You could put a 3 in it. You could put a 4th root in it, whatever it happens to be. As you advance in your mathematical journey, you will start to use this symbol as well. But looking at this first question, question 1, we have square root of 27 here. Now, we get this really long irrational decimal, right? It's 5.1. And so if I look at the two perfect squares, this falls in between. 27 falls in between square root of 25, which is 5, and square root of 36, which is 6. So this makes sense, right? 5.196152, etc., etc. Now, when we go to round this, we are then looking at the hundreds place, which is the 9, and you are going to look directly after that to determine how to round it. Now, in the thousands place, we have the number 6. So that's bigger than 5. That's, in other words, past the midway point for that number. So we would actually round this up to the next place after that, which in this case, 9 actually would round up to 10. So we actually even need to go to the next place here, to the 10th place, and that becomes a 2. So in other words, this would round to 5.20, 5 and 20 hundredths, or you could even just leave it as 5.2, 5 and 2/10, depending on the particular structure a quiz might be asking for. The second question then we have is square root of 52, or radical 52. So again, we look at our radical symbol, the number underneath 52, the radicand, we then would type in 52, and we get this nice irrational decimal here. We again are going to round to the hundredths place, 2 decimal place after, and to determine what to round to, we are then looking at the thousandths place. So in this case, we have a 1 in the hundredths place and a 1 in the thousandths place. So in this case, we're rounding down to 7.21. So our answer for this would be 7 and 21 hundredths as our answer. Now we're adding a variable to the mix, and we're asked to simplify variable expressions with square roots. So starting with question 1, then we have the square root of 64x squared here. Now, we have to remember what a square root symbol is really doing, and what it's doing is basically finding the base number of a squared number, right? In other words, we're kind of looking at the duplicate, essentially. So if I look at 64 and I was to expand these numbers out, the square root of 64 really is 8 times 8, right? So the base number here is 8. Now the base number for x squared would just be x. So this is really x times x. Now, once I take the square root of this particular expression, you are essentially eliminating one of the duplicates. So you're eliminating one of the 8's and one of the x's. And then when you take it and you rewrite your solution, you would simply write this as 8x here. Okay, and that's it. All right, let's look at question 2. So question 2 is interesting because it has the negative on the outside of the radical sign. In this case, that's fine. You can do that. This isn't a no solution one. If the negative was on the inside, then it would be a no solution. And basically that negative symbol will then be dropped into the answer at the end. But if I rewrote that question here, I have square root of 81 y squared. Now, if I was to rewrite this with kind of an expanded form here, looking at the actual base numbers for these, we would have 9 times 9 is 81 times y times y. Now, once I took the actual square root of this, I'm eliminating my duplicates. So I'm eliminating one of the 9's and one of the y's. So then when I was to rewrite this, I would simply write this as 9y. And I would also drop down that negative symbol here, and I'd simply write this as 9y. The final set of questions then use square roots in applications. So some word problems here. So in question 1, Maria wants to make a square garden. So we're going to pretend this is a square garden here, and that's all equivalent sides. And she has enough soil to cover an area of 225 square feet. So basically, on the inside of the square, we're looking for feet. We have feet squared in this case. So in other words, we're asked to find how long each side of the garden can be. In other words, what we're really asked to find is what the side length is that allows us to get equal to 225. So if I was to write an equation here, really the equation is s squared for side is equal to 225. Now to actually solve this equation then, you would take the square root of s squared and you would take the square root of 225. And once you took the square root of each of these sides, you would get s is equal to 15. So in other words, each side of this square is 15 feet in length here. Okay. So taking the square of the area, another way to kind of shorten up this formula, and what they have in the textbook is actually just a square root of the big letter A standing in for area. Now, question 2 is a gravity type problem that's defined in the textbook. So it reads, a helicopter dropped a supply package from a height of 1,600 feet. How many seconds did it take for the package to reach the ground? So on first glance, this question might be like, is there really enough information to solve it? Well, there is a formula for gravity and figuring out something for time. So time is really equal to the formula h, which stands for height, divided by the number 4. Okay, so this is a gravity type formula that's been calculated. So what you then do is, once you know the height here, you can simply input that number into your formula. So it would be 1,600 divided by 4 now. Okay, and once you take the square root of 1,600, the square root of 1,600 is equal to 40. So then we have 40 divided by 4, which then is equal to 10. So in other words, it takes a total of 10 seconds for our package to fall 1,600 feet here. Okay, and we're done with question 2. So when you come across these types of questions, that is the type of formula you will be using. All right, so we have covered chapter 5.7, Simplify and Use Square Roots from the OpenStax Pre-Algebra textbook. I would go ahead and now get into the textbook, which I've linked in the description of this video, do a few more problems. If you come across anything you don't understand, feel free to ask that question in the comment section below. Otherwise, I hope everyone does well with this. Good luck, and I will see you in the next video. Thanks, everyone.